Hello, in this video we're going to compare the Rankit plot versus a QQplot. Now QQplot is a default function in R that plots your sample data against what is expected in the standard normal distribution. And if your data is normal, then it should be a straight line, and if it's not, then you get a deviation from a straight line. And a Rankit plot is another type of normal probability plot. It's less known, but before we start, rankits are used in the Shapiro Wilk Normality Test, and it's actually one of the most powerful tests in detecting normality or not. Now, Rankit is an odd name, and it's I forget the statistician's name, but it's the same statistician that named or coined the term probit. So he coined this term Rankit. And the definition off of Wikipedia, which I think after you see the example will make perfect sense. A rankit of a set of data are the expected values, the order statistics of the sample from the standard normal distribution of the same size as the data. And so let's go through this example. Um, the we're going to use the same 6 data points from the um, Wikipedia page. So here are the data sorted. Now, if this follows a normal distribution, if the data follow a normal distribution, then maybe, and we're going to try to sprinkle those down onto the standard normal distribution. So how do you do it? Well, you might think half of them should be negative and the other half positive, right? If it's truly a normal distribution, expect maybe half and half. But but where does 16 go? Should it be the 10th percentile, the 20th, the 5th percentile, in that standard normal distribution? So all these probability plots, that's the goal of, what does each of these values represent in that standard normal distribution? And there's dozens and dozens of normal probability plots. And in my personal opinion, is the Rankit plot and the QQ plot are probably the two most popular. So what we want to do is that's our y data. So when we plot it, we need x's. And the x's is going to be a vector where the first component represents the mean of the first order statistic. Now, that's assuming that our data follows a standard normal distribution. And the second component in our vector, which corresponds to this number 22, is going to be the mean of the second order statistic from a sample of size 6 from a standard normal distribution, and so on. The x vector are called the rankits. It's a vector of rankits. It's the mean of the order statistics. And again, our goal is to plot x times y, and it should be a straight line. Well, to calculate the mean of these order statistics, we need the density for the j'th order statistic. And we're not going to go through that in this video, but this is the density for the j'th order statistic. And so F would be the standard normal density, and F of x here and here would be the CDF of that standard normal distribution. Now I have a function here that I call rankits, and in that function it creates a function here. I've highlighted it, which is this density, right? This blue part, right? P norm is the CDF raised to the j minus 1. D norm is the density. 1 minus P norm, which is the CDF raised to the j minus 1. So it's the same. I've just put in an extra x because we're taking the mean. And so you need it x times that density integrated over all possible values. And so that's what we do in here. So for 1 to n, so we're going through each observation in the sample, then we're going to integrate this function over that infinite, from negative infinity to infinity. So let me load this. And then let's just look at the first 6 rankits. And so this is it. So these are values in the standard normal density distribution. And so, right, the left three are negative, the right three are positive, and so we think these represent the 6 values in our sample, assuming they came from a normal distribution. So now we plot it, and this is what it is. So the bottom here, the mean of the order statistics, called the rankits, and this is our actual data. And notice that it's very, straight line-ish. So I don't think it departs from a straight line much, which says that our data might follow a normal distribution. Now let's plot a few more rankits. We're going to plot the rankits of a sample size of 88, and our sample we're going to grab from a t-distribution with 2 degrees of freedom, and then look at that. So this is it. So notice that it's straight line-ish in the middle, but then the tails deviate quite a bit from a straight line, and that's just expected because a t-distribution with 2 degrees of freedom has very heavy tails, and so it shouldn't be a straight line. So there's obvious deviation from a normal distribution here. Now let's plot the rankits versus a t-distribution with 44 degrees of freedom. Now 44 starts becoming more and more standard normal like, and so let's look at that. And so here, notice that it is sort of straight line-ish, and even these are pretty good. And so I'd still consider that it's pretty close to a standard normal, using the Rankit plot. Now a quantile plot, QQplot, is also a default plot in R, and let's look at that. And that's what this is. And it also has a line function, so it fits the theoretical slope to that. Now the y-axis is our data. That hasn't changed, but now what each of these data points represents in the z distribution has changed. So these values have changed. It looks very similar, but the way that it thinks about it has changed. Okay, so first of all, let's just look at what those x values are. So in the QQ norm, we're going to not plot it, but we're going to just grab those x values and compare them with the rankits that we just plotted, or the calculated. So the rankits on bottom, these are the mean of the order statistics, right? And then these quantiles up here are something, which I'll talk about in a second. But notice that they're close. Very close in this case. 1.28, 1.26, those are all very close. And actually pretty much every normality plot that is calculated are all going to be, very close, cousins to each other. So the question is, how does R pick the quantiles for the normal distribution? So let's look at our data again. So here's our data, these 6 data points down here. What does 16 represent? Does it represent the 5th percentile of a standard normal, the 10th, the 20th? How do you pick that? Maybe let's look at what percentile it is in the sample. So if we just look at that, so 16 is roughly the 17th, percentile. 22, the 2 out of 6 is 33%. 65 out of 6 is 83%. 75 is 6 out of 6 was 100%. So now the difficulty of just using that type of reasoning is when you get to 6 out of 6, the 100th percentile in a standard normal distribution is infinity. So you can't quite use this naive way to do it. So how do they do it? So what we do, I'm going to show you, is the QQ norm, which is the QQ plot. I'm not going to plot it, but I want to grab the x values from these. So those create the z values. Then I want to use P norm, which is the CDF of a standard normal, and look at what it creates. And it creates this vector. So QQplot is thinking that 16 represents the 10th percentile. 22, which is 2 out of 6, represents the 26th percentile in the standard normal distribution. 40 represents 42%, and so on. 75 represents that 90th percentile, and it's actually symmetric. It's 10% in the tail, 10% in the tail, 26% in the tail, 26% in the tail. So that's how QQ norm does it. It has a formula that says, if this is from a normal distribution, we have a sample size of 6. The smallest, usually represents about the 10th percentile. The largest is about the 90th percentile. Now the question is, what's the formula? And this is the formula. It's I minus A divided by N plus 1 minus 2A. And this is pretty much the formula that every QQ plot uses. The difference is, how do you pick A? Now notice that even on SAS and all your help, websites, they'll use a formula Z of, and then use this crazy formula. And what it represents, Z, is actually the value in the standard normal distribution, but it's a function of this crazy formula. Now what R uses is, if N is less than or equal to 10, it uses A of 3/8. If it's more than, the sample size is more than 10, it uses A of 1/2. And actually I want to go to the website for QQ plots, and this is a Wikipedia page. So QQplot, and then it explains it, and it does a great job. And then it says, you know what, lots of people use different formulas, and that's what this represents. And I'm sure the corresponding author thinks their formula is best or does a great job. Now this highlighted part here is what R uses when the sample size is 10 or less. If it is more than 10, it uses this formula. And so R is using, two of these, depending upon what size the sample you use. Okay. So now let's prove that. So since our sample is 6, which is less than or equal to 10, A is 3/8, and I'm going to let I be, 1 to 6, which represents, which data point. And then I put them into this formula, and look what it produces: 10, 0.10, 0.26, 0.42, and etc. And let's see, and then let's put those quantiles in the Q norm, which is the inverse CDF. So it takes those quantiles and pops out a Z value for them, which is this. Now let's do the same thing and use the QQ plot, or they call it QQ norm, and see what X values it calculates. And notice that they're 100% the same, because that's the formula that they use, and that's it. Well, that's the difference between the Rankit plot and the QQ plot. Now, one last thing, which will take about a minute to explain. In normal probability plots, they all think about it the same way, and that you have a sample of size N, and if you were to sprinkle those down onto a standard normal distribution, roughly where would they fall? And that's the goal of a normal probability plot. Then when you plot it, it should be a straight line. If they deviate, then it's not. And so we have learned two of those things. One thinks, well, they get put down into the Z distribution based upon some formula that drives the quantiles, the position of that data, the data in the sample data. That's the QQ plot. One says, let's just look at the mean of the order statistics of the position in the sample, and that's the Rankit. But another approach is to use the median of that order statistic. And so I've created another function here which calculates the median of that order statistic. So it goes in and finds the median of the first order statistic, the median of the second order statistic, and etc. to the median of the nth order statistic. Now I'm not going to go over it, but I'm going to include it in the program and in the comments if you want to mess with it. And what I want to do is compare the Rankits versus the medians of, say, a sample of size 6. and these are it. So the rankit is on the top and the median of the order statistic on the bottom, and they're all going to be close. All these normal probability plots are. Now let's do rankits for a sample size 11 and the medians of the order statistics of a sample size 11 and compare those. And again, they're all, they're close. And if we were to compare the QQ plot for this, it would also be close, but I think due to time I'm not. Well, hope you enjoyed that. Next video I'm going to derive the test statistic for the Shapiro Wilk test, and it involves rankits, and so I wanted to introduce rankits before I jumped over into that one. Well, thank you. Hope you enjoyed it. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.